It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we wrestled with the very concept of intelligence. We explored its different facets, its biological roots, and the philosophical challenges of even defining what we mean when we say something is smart. It's a slippery, ambiguous, and deeply human concept. Today, we travel back in time to the precise moment that humanity decided to take that slippery concept and make it an engineering problem. The year is 1956. Elvis Presley's Heartbreak Hotel is topping the charts. The anxieties of the Cold War permeate daily life, but on the quiet, picturesque campus of Dartmouth College in Hanover, New Hampshire, a small group of scientists is gathering. They aren't just building better calculators. They are laying the groundwork for a machine that could learn, reason, and, perhaps, think. They are about to give this audacious dream a name: artificial intelligence. This is the story of the summer that started it all. Our objectives for this episode are critical to our entire curriculum. First, we will meet the four founding fathers of AI: McCarthy, Minsky, Rochester, and Shannon. Second, we will investigate why the term artificial intelligence was chosen as a deliberate break from the past. And third, and most importantly, we will deconstruct the grand conjecture from their original proposal. An idea so audacious, so profoundly optimistic, that it has fueled this field for more than half a century. If episode 1 was about the what, this episode is about the when and who. This is the origin story. This is where the map for our entire journey is first drawn. To truly understand the importance of 1956, we have to set the stage. We are in the mid-1950s. The world is still breathing a collective sigh of relief after World War II. The first digital computers, like ENIAC and UNIVAC, are just a few years old. These are not desktops. These are giant brains, room-sized behemoths of vacuum tubes and relays. The public perception of these machines is a mixture of awe and terror. They are number crunchers, but the idea of them thinking, well, that was mostly science fiction. Mostly. Because in 1950, Alan Turing had already published Computing Machinery and Intelligence, famously proposing the Turing test, so the idea was in the air. But the research was fragmented. It was scattered across different departments and different names. You had automata theory, with deep roots in Turing's work. This was the formal study of abstract computing devices. Think of it like a very, very complex vending machine. You put in a coin and that's the input. You pull a lever and that's the state change. And it delivers a product which is the output. It's theoretical, it's mathematical, but it doesn't really capture the fluid, messy nature of learning. Then you had the dominant, cool field of the day, cybernetics. Pioneered by the brilliant and charismatic mathematician Norbert Wiener in the 1940s, cybernetics was a grand interdisciplinary theory focused on communication and control in both animals and machines. Its central insight was the feedback loop. The classic analogy is a thermostat. It senses the room temperature, which is the information. Then it compares that to its goal, which is the set temperature. And if there's a difference, that's the error signal. So it takes an action, like turning on the furnace. The furnace's action then feeds back to change the room's temperature, which the thermostat senses again. This was a powerful idea. It explained how guided missiles worked, how biological systems maintained homeostasis. It was a bottom-up approach, seeking to understand self-organizing systems. But to some researchers, cybernetics felt limited. It was heavily focused on biology, on analog signals and continuous feedback, not on the crisp, logical, step-by-step reasoning that seemed to define human thought. It was more about reacting than thinking. Into this fragmented landscape steps our first key figure, John McCarthy. McCarthy was a young, brilliant, and intensely driven mathematics professor at Dartmouth College, and he was dissatisfied. He had co-edited a volume on automata theory and felt it missed the mark, and he particularly felt that cybernetics, with its emphasis on analog systems, was misguided. He wanted to create a new, distinct discipline. He envisioned a top-down approach, believing the essence of thought was not in the biological wetware of the brain, but in the abstract manipulation of symbols, according to the rules of logic. So, he made a pivotal strategic decision. He coined a new term, artificial intelligence. This was a deliberate act of separation, a declaration of intellectual independence. He later stated his motivations quite clearly. He said, "One of the reasons for inventing the term artificial intelligence was to escape association with cybernetics. Its concentration on analog feedback seemed misguided, and I wished to avoid having either to accept Norbert Wiener as a guru or having to argue with him." This wasn't just semantics. It was a fundamental schism in philosophy. By nailing this new flag to the mast, McCarthy was elevating the logic-based, symbolic paradigm. But a young professor can't just snap his fingers and convene the brightest minds. He needed a dream team to co-sponsor the proposal, and he assembled an absolute monster of a team. First, he recruited his friend from his Princeton days, Marvin Minsky. Minsky was a junior fellow at Harvard, guided by the conviction that the brain was a machine whose functions could be replicated, and he was a builder. In 1951, he had already built the SNARC, which stands for the Stochastic Neural Analog Reinforcement Calculator. It was the world's first artificial neural network learning machine, a sprawling, room-sized device made of 3,000 vacuum tubes, and, get this, a surplus automatic pilot mechanism from a B-24 bomber. It simulated a network of 40 neurons that could learn to solve a maze through reinforcement. Minsky represented the bottom-up, brain-inspired approach, the very cybernetic ideas McCarthy was trying to escape. This, by the way, shows you the sheer intellectual diversity of this founding group. Second, they needed practical, real-world muscle. They got Nathaniel Rochester. Rochester was the senior statesman of the group, the manager of information research at IBM. This was a crucial move. Rochester was the chief architect of the IBM 701, the company's first mass-produced scientific computer. He was a practical engineer who brought industrial credibility and, most importantly, the link to the powerful hardware that would be needed to run these experiments. And finally, they needed a legend. They needed a name so respected that nobody could ignore the proposal. They got Claude Shannon. It is difficult to overstate the importance of Claude Shannon. A mathematician at Bell Labs, he was already revered as the father of information theory. He was also famous for his eccentric brilliance, known to juggle while riding a unicycle through the halls of Bell Labs. In 1948, he had published A Mathematical Theory of Communication, the paper that essentially invented the bit. Before Shannon, information was a vague concept. Shannon provided the mathematics to quantify it. He showed that information was a measurable, physical thing. Shannon's participation gave the proposal immense intellectual weight. He had already written papers on programming a computer to play chess. His work provided the theoretical toolkit to frame intelligence, language, abstraction, learning, as problems of information processing. So, in August of 1955, this dream team of McCarthy, Minsky, Rochester, and Shannon drafted a 17-page document. The title, A Proposal for the Dartmouth Summer Research Project on Artificial Intelligence. They submitted it to the Rockefeller Foundation, asking for a modest, almost quaint, $13,500 to cover the entire summer. But the ambition contained in those pages was anything but modest. It was centered on a single, powerful, and profoundly radical idea. The proposal began with this sentence, which I want you to hear very clearly. We propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. This is the grand conjecture. This is the philosophical core of the entire endeavor. Let's deconstruct it. The study is to proceed on the basis of the conjecture, a conjecture. They are admitting this is a hypothesis, it's an unproven starting point. This is the scientific method in action. That every aspect of learning, or any other feature of intelligence. This is the scope, this is the ambition. They are not saying some parts of intelligence, like arithmetic. They are saying everything. Language, creativity, perception, common sense. They are throwing down the gauntlet. They are saying all of it is on the table. Can in principle be so precisely described. This is the philosophical bombshell. This is the statement that intelligence is not magic. It is not a divine, unknowable spark. It is a process, a complicated one to be sure, but ultimately it is a process, a set of rules, operations, and mechanisms that can be described, and not just vaguely, but precisely, as in with mathematics, with logic, with an algorithm. This, by the way, has been called a psychological wager. It was a bet that human thought could be reframed, moving it from a mystical event into one node in a continuum of possible intelligences. It's the ultimate reductionist, materialist, computationalist view of the mind. If you can describe it precisely, then you can, in theory, program it. Which leads to the final clause. That a machine can be made to simulate it. And there is the engineering mission, the call to action, the goal of the entire field laid bare. If we can describe it, we can build it. Think about the audacity of this. This is the single most optimistic, ambitious, and, let's be honest, hubristic statement in the history of modern science, and it is the engine that has powered AI research ever since. So the grant was approved. Well, half of it was, and in the summer of 1956, a small group of researchers convened in the mathematics building at Dartmouth. Now this leads us to our first major misconception about the Dartmouth workshop. The common story, the legend, is that this was the Woodstock of AI, or the Constitutional Convention of AI, a magical summer where these brilliant minds all collaborated, had massive breakthroughs, and emerged with the first intelligent programs. The reality was a lot messier. It was not a unified 8-week boot camp. The grand vision of a unified effort largely failed to materialize. These were all brilliant, established, and, let's say, confident researchers. They had their own agendas. Attendance was sporadic. People dropped in and out. Of the core group, only John McCarthy, Marvin Minsky, and another brilliant young researcher named Ray Solomonoff were present for the entire summer session. Claude Shannon, reportedly, was a bit by the whole thing, and spent a lot of his time juggling and working on his own projects. The most significant event of the summer, the one that came closest to a breakthrough, was not a product of the workshop's collective effort. It was a demonstration of work that had already been completed. The stars of the show were Alan Newell and Herbert Simon, researchers from Carnegie Tech and RAND. They visited for just a few days, and they brought their groundbreaking program, The Logic Theorist. The Logic Theorist was designed to prove mathematical theorems from Principia Mathematica. It was the first program ever created to mimic human problem-solving skills, using heuristics and symbolic reasoning. And it worked. It independently discovered a proof for one of the theorems that was more elegant than the one the original authors had published. The demonstration was a stunning proof of concept for the grand conjecture. It provided tangible evidence that a machine could perform a task that was, until then, a hallmark of human intellect. So if the workshop itself was a bit of a letdown, why are we dedicating an entire episode to it? Why is it considered the founding event of AI? Because the true significance of the Dartmouth workshop was not the problem solved, it was the community formed, and, most importantly, the agenda set. It was the first time this disparate group of thinking machine researchers were all in one place, focused on one idea. By coining the term artificial intelligence, McCarthy had created a banner. He gave the pursuit a name. And that agenda was literally written into the 1955 proposal. The document laid out 7 topics for study, and this list, looking back, is astonishingly prescient. It's the blueprint for the next 70 years of AI. They listed first, automatic computers, the basic need for faster, better hardware. Second, how can a computer be programmed to use a language? That's the entire field of natural language processing, or what we now call NLP. Third, neuron nets, the study of brain-like networked structures, a direct line to the deep learning of today. Fourth, theory of the size of a calculation, the exploration of computational complexity, a core of computer science. Fifth, self-improvement, the radical idea of a machine learning from experience. We just call that machine learning. Sixth, abstractions, the challenge of forming abstract concepts from raw data, a key problem in computer vision. And seventh, even randomness and creativity. The workshop's true success was not in the answers it produced, but in the enduring power of the questions it asked. It took the vague notion of a thinking machine and gave it a structure, a vocabulary, and a scientific agenda. And most importantly, the workshop and its participants laid out the 2 great, divergent paths that AI research would follow for the next 50 years. These are the 2 family trees of AI, and understanding them is essential to your AI literacy. The first path, the one championed by John McCarthy, Alan Newell, and Herbert Simon, is what we call symbolic AI. This is the neat approach. The philosophy here is that intelligence is symbol manipulation. Just like in logic or algebra, the human mind, in this view, is a symbol processing system. We have rules in our heads, and we apply them to symbols. The logic theorist was the perfect example. It didn't understand logic. It just had rules for manipulating symbols. Analogy time. Think of symbolic AI as a master chess program. It has a perfect digital representation of the board, which are the symbols. It has a perfect list of the rules, like how a knight moves, and it has an algorithm to search through all possible future moves. If I move pawn to e4, then he can move knight to f6. It calculates millions of these symbolic possibilities and picks the best one. This is a top-down approach. You start with the high-level rules of intelligence, and you program them in. This path, energized by the logic theorist, led directly to what's now called the golden age of AI. From the late 50s to the 70s, the confidence was palpable. Researchers predicted a fully intelligent machine in less than 20 years. This attracted significant funding from agencies like DARPA, establishing major AI labs at MIT and Stanford. A direct outcome: John McCarthy, now at MIT, developed the Lisp programming language in 1958. Lisp, which stands for list processing, it was a language designed specifically for this symbolic, rules-based approach. It became the lingua franca of AI research for decades. This path led to expert systems that could diagnose diseases, and to programs like SHRDLU that could understand commands in a simple, blocks world. But this unbridled optimism also contained the seeds of its own demise. The grandiose objectives set impossibly high expectations. As researchers moved from simple microworlds to complex, real-world problems, they ran headlong into a brutal wall, a problem we call combinatorial explosion. An analogy? Our simple chessbot is one thing, but LifeBot, the number of possible moves in a real-world conversation or in identifying an object in a cluttered room, isn't in the millions. It's astronomical. It's practically infinite. The computers of the era, their limited power and memory, simply couldn't handle it. The promised breakthroughs failed to materialize. By the early 1970s, funding agencies grew skeptical. Critical reports, like the Lighthill Report in the UK, concluded AI had failed to live up to its promises. Funding was drastically cut, and the field plunged into a period of stagnation, the first AI winter. But there was another path. A quieter, messier, less dominant path. The path championed at Dartmouth by our other founder, Marvin Minsky. This is the connectionist approach. This is the scruffy approach. The philosophy here is completely different. It says that intelligence isn't about high-level, pre-programmed rules. That's not how brains work. A baby learning to recognize its mother's face isn't following a logical script. The connectionist philosophy says intelligence emerges from the bottom up. It emerges from the complex, interconnected network of billions of very simple processors, our neurons. A single neuron is dumb, but connect 86 billion of them in the right way, and you get us. So the connectionist goal wasn't to program rules, it was to simulate the structure of the brain, to build an artificial neural network, like Minsky's SNARC, which learned through reinforcement. It's not programmed, it's trained, it's messy, it's scruffy. So at Dartmouth you have these two fundamentally different paradigms sitting side by side. First, symbolic AI, the NEATs. Intelligence is logical, symbolic, and top-down. We program it. Second, connectionism, the scruffies. Intelligence is statistical, emergent, and bottom-up. We train it. So what happened? In the short term, the symbolic NEATs won, and they won decisively. The logic theorist was concrete proof. The scruffy approach was too computationally expensive and poorly understood. In fact, in a famous and some would say infamous move, Marvin Minsky himself, along with Seymour Papert, published a book in 1969 called Perceptrons. This book brutally, mathematically, exposed the deep limitations of the simple, single-layer neural networks of the day. This book was so influential that it helped ensure the AI winter, at least for the connectionists. Funding for neural network research dried up for almost 2 decades. The scruffy path went into a deep hibernation. So let's connect this to today, right now. Why does this 1956 history matter? Because that scruffy connectionist path, the one Minsky played with and then helped bury, it came back. In the 1980s, new breakthroughs showed how to train deeper networks. And in the 2000s and 2010s, we got two things: massive amounts of data, like the entire internet, and massive computational power, thanks in large part to gaming GPUs. Suddenly, the scruffy approach could be scaled up into deep neural networks with billions of connections. Every single piece of modern, revolutionary AI you encounter is a direct descendant of that scruffy connectionist path. The AI that recognizes your face, a convolutional neural network. The AI that translates languages, a transformer network. The large language models. The generative AI that write poetry and code, those are massive transformer-based neural networks. They are all the children of Minsky's SNARC. They are not programmed with rules. They are trained on data. The Dartmouth workshop didn't just name a field, it gave birth to the two great families, the neats and the scruffies, that would fight for dominance for the next 60 years. So, what have we learned? We've learned that artificial intelligence is not a timeless scientific term. It's a brand name. A brilliant piece of marketing coined by John McCarthy in 1955 to unify a fragmented field and give it an audacious goal. We've deconstructed the 1956 Dartmouth workshop. We've corrected the misconception that it was a constitutional convention. It was, in fact, a disjointed but foundational event that served as a declaration of independence for a new science. We've met the four founders and seen their diverse, even contradictory, contributions. We've learned that its legacy is double-edged. Its visionary optimism created the field, but also created the cycle of hype and disappointment, the AI winters that has characterized its history. And most critically, we have engraved the grand conjecture into our curriculum. The belief that all of intelligence is, in principle, describable, and therefore simulatable. This is the philosophical bedrock of our entire course. Now, we can see our path forward. We've seen the birth of AI. In our very next episode, we are going to follow that golden age symbolic path through the 1960s and 70s, when the field experienced its first great wave of optimism and funding. We'll explore the programs that came from it, like SHRDLU and the expert systems, and then witness how this unbridled confidence led to the first AI winter, a period of disillusionment and funding cuts that would shape the field for decades to come. Your takeaway for today is this: when you see the letters AI on a product or in a news article, I want you to pause and think of that summer in 1956, and then ask yourself a simple question. Is this AI neat or scruffy? Is it operating on a set of explicit, human-programmed rules, or is it a scruffy connectionist system, a trained neural network that learned its own rules from massive amounts of data? By simply being able to ask that question, you are already moving from I-curious to I-literate. The true legacy of Dartmouth wasn't a program or even a single paper. It was the breathtaking confidence, the intellectual audacity, to look at the human mind, the most complex phenomenon in the known universe, and declare it a solvable problem.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.